Greetings and welcome back. Today's vignette is a continuation of the couple we've been doing so far. The first one on representations, the second one on vectors. And in a certain sense, it all culminates here, where we are today, which is the deep, deep question of what are the best, with quotes on the word best, but best coordinates, best degrees of freedom, best collective variables to describe some particular situation, process, structure, phenomenon, and also a related topic, which is what I'm going to refer to as data collapse. And you'll see what I mean by that. I'm showing you an example right here. And I love referring to this as the awesome power of data collapse, which I will explain in a moment. So just to reiterate, really, the thing that I'm extremely motivated about here is this idea of best coordinates. So, I think there are many, many contexts in which we encounter some situation in the external world and we want to describe it. And in so doing, we are forced to ask ourselves the question, what are the best coordinates? This person that I'm showing you here is a very famous figure in the world of modern cell biology. His name was Ira Herskowitz, and I did a little bit of digging. I'm not entirely sure that I can get the actual correct place where he made this statement, but the comment was the awesome power of yeast genetics. And I think that that's true. Yeast genetics more generally, has an awesome power for seeing the unseeable, previously unseeable, and really learning things about it. It goes back to Mendel. And I just want to say that this notion of data collapse is another such example. So the question that I have in mind here is, for starters, what are the right degrees of freedom? And we're going to come back to this one in great detail in one of the next vignettes. But the key point here is that I can decide on coordinates for describing some situation of interest. And if the coordinates are bad, with quotes on the word bad, then that means that my equations are messy. That means that, for example, in this case, what I want you to notice is that the two differential equations for the motion of mass 1 and the motion of mass 2, that they're coupled. What do I mean by coupled? I mean that the variable x2 here appears in the equation for x1 and vice versa. So, interestingly, there's a choice of coordinates, which is what we'll work out in one of the upcoming vignettes, and I can even hint at that here. Take a look. If I add these two equations, so if I add them, then what I will get is m d squared by dt squared, x1 plus x2, and that's going to give us, let's see what we will find. We will find a, let's see, I have minus 2kx1, so I get a minus k, and then an x1 plus x2. And that actually jibes with our expectation. Why would I say that? Because if I have x1 plus x2 as my coordinate, that means that both objects are moving like this, back and forth, and that means the central spring is not stretched. And the reason that that's important or interesting is that means that the two masses behave as though they're independently attached to their spring of spring constant k. So the symmetric sum x1 plus x2 is a better natural coordinate. Now let's try that again, and this time let's take the difference, and what we'll see there is m d squared by dt squared of x1 minus x2, and that's going to be equal to minus 3k x1 minus x2. So that's a second equation, and note that the variable x1 minus x2, the equation featuring x1 minus x2, is closed in the sense that it doesn't couple to the x1 plus x2. What we've done is essentially through sort of a simple scratch and sniff approach, we found what I would call the normal modes, or the correct collective coordinates. Here's another example. So if I take a book and I throw it up in the air, if I throw it along a good coordinate system, if I have it's oriented in the proper symmetry, then it will rotate about that axis without change. So those are the good coordinates. The language that we would use to describe that in mechanics is to say that we have found the diagonal representation of the moment of inertia tensor. And so, again, my point is that we have the possibility of finding good and bad coordinates, if you'll let me use those words, which are maybe a little bit too judgmental. But the point is that it's way more convenient if we find a coordinate system in which our equations exhibit themselves in the simplest form. And there are many examples of this that we use all the time. So let me try to give you a little bit of a sense of now what I have in mind about the natural or good coordinates in the context of a problem that we've already thought about before and which comes up all the time, which is the probability of occupancy of a receptor by its ligand. So the way that we're going to think about this is I'm going to say that P bound, the probability that this thing is bound, as a function of the concentration of ligand is going to be equal to maybe I will prefer to write this actually as a function of the ligand in this way, that it's going to be equal to the concentration of ligand receptor over the concentration of receptor plus ligand receptor. Okay, what have I done here? I've essentially invoked the definition of what we mean by a probability. The numerator is all the favorable outcomes, and the denominator is all the outcomes. The reason I say all the outcomes is that this object downstairs is the total number of receptors. There's only two choices. They're either empty or they're bound. So that's all the receptors. And LR is the class of receptors that are occupied. Now I invoke the definition of the KD, which we've talked about earlier in other vignettes, which is a measure of the equilibrium between the bound state and the free ligand and receptor states. And I can use this to solve for LR as L times R over KD. Substitute that then up here. And what you will find is actually this. Okay, except it will be, in our language, it will be P bound is equal to L over KD over 1 plus L over KD. Now, why do I go through all this trouble? Because the way that you might be tempted to plot this if you were to pipette into some solution and measure the occupancy of a receptor is you might be tempted to plot on the x-axis the ligand concentration that you pipetted. And my argument here is that that is not the correct variable or not the best variable. It makes it appear that every receptor is its own adventure. You know, each one of these curves is a different curve. Note that KD is the concentration at which we get half saturation. If you look at this, KD has units of concentration. If I plug in L is equal to KD, then I find P bound as a half. That corresponds to exactly the point at which the entropy, which is reduced by binding, is equal to the energy gain upon binding. It's literally exactly that point. And so each one of these is its own adventure. My point is, the receptor doesn't care about what we pipette. The receptor has its own natural coordinate system, or its own natural measurement of concentration, and that measurement is KD. So the point is if I elect to now plot P of x, which is x over 1 plus x, all of my curves collapse on one curve where I've defined x is equal to L over KD. So this is a classic, perhaps the simplest example that I can think of data collapse. It's profound, and it has a much bigger lesson than the particulars of this one. Again, let me just reiterate. What is the lesson? The lesson is that there is a natural variable for describing this, not the pipetter's variable, but the natural variable, which is, if you like, you need to shift into the coordinate system of the receptor, and the receptor sees the world in terms of its KD. Okay. So there are many examples of this kind of thing. So in the 1940s, if I remember correctly, there was this beautiful thing done by Guggenheim, and this is kind of shocking if you really get down to it, because and note, I guess I cut off this thing. That should be this should be T over TC, so I apologize for that. So what you see is that basically we get the same equation of state for a bunch of different elements. I also see another mistake here. This is argon, so that I'm also sorry for. And the point is that, at first cut, you, once again, like I said in the previous case, you might be tempted to think of each element or each molecular species as being its own separate adventure. And yet, when we use the right coordinates, what we find is that there's a universality to the equation of state. The same kind of thing has been seen in the context of the theory of phase transitions. What I'm showing you on the right is scaling, basically a collapse of magnetization data from a bunch of different kinds of magnets. And what I'm hoping is that you'll be impressed by this, because, again, I think the temptation, it's very easy to have this notion of material specificity, that every example is its own adventure. And the whole essence of this particular vignette is to argue, A, that there is such a thing as convenient or best or most intuitive or most revealing coordinates. That's point one. And often, when one finds those natural coordinates, what we find is that what was ostensibly a material-specific sort of response curve all collapses onto one master curve. This kind of notion of data collapse it transcends any particular part of science. It's some beautiful work that was done by Sri Iyer Biswas, in which what they were looking at, if you like, is the time to division. On the lower right, you can see cells. This is Colobacter, I think, if I remember correctly, grown at different temperatures. And the point is that there's a trajectory. In other words, you can watch a cell from moment of birth until moment of division, and you can measure that time scale, and it will depend on temperature. And yet what they found is shown on the lower left, which is you can collapse all of that data onto one universal master curve. My last example has to do with chemotaxis. And I just wanted to harken back to experiments done in the late 1800s, which is using what I think of as like kind of a living spectrophotometer or a living prism or whatever. The idea is that one separates light into its component wavelengths using a prism, and there's a microscope cover slip that's full of algal cells, and they move in response to the presence of oxygen, etc. And all I really care that you see here is that there's a preference for certain positions, and those positions correspond to certain wavelengths. So we know that microscopic organisms, single-celled eukaryotes and prokaryotes alike, exhibit preferences, if you'll let me use that word. And I think it's a proper word, although people can get triggered by such language. So I think it's a proper language. They have preferences, and in response to the environment that they find themselves into, they exercise those preferences by how they move. And in the case of chemotaxis, I've already talked about it in previous vignettes. I'm not going to belabor it. And also, I think it's part of the ether of our field. Most people that think about the connection between biology and physics or biophysics will for sure know about this hydrogen atom of signaling and regulation. So just a reminder, the cells do a run and tumble and run kind of motion. They go about 30 microns on a given run. They go off in different directions, and if the direction is good, they might go in that direction for longer. I'm not going to belabor it, but there is a circuit that has been figured out on the basis of genetics and biochemistry and many other approaches, biophysics, the work of Howard Berg and many of the people that have worked with him. We know that there's a circuit, and by using fluorescence, they could measure the action of this circuit, which essentially tells the motor, do you or do you not change to rotating in the opposite direction, leading to a tumble. And so what's shown on here on the left and on the upper part is, I'm not going to get into the technical details. I recommend that you go look at my earlier vignettes, look at Physical Biology of the Cell, or alternatively, go read the papers by Sorek and Berg. There's two in particular, I think both in PNAS from the early 2000s. Super elegant, super interesting. And what they did is they measured the activity of this chemical messenger. Again, I'm not going into details. As a function of the chemoattractant, which is shown on the right, on the x-axis is methyl aspartate. The details, again, don't really matter for what I'm trying to get across here. And they had a bunch of different mutants for reasons that are super smart, super interesting. What are the general reasons? They're trying to figure out, how these excuse me, how these molecular systems adapt. If I change the ambient concentration of methyl aspartate at a constant value, meaning there's no gradient, temporarily I can trick the cells. They will think, if I make a jump in the concentration, they will think they're in a gradient, but then they will realize they're not in a gradient, and they will go back to sort of the same response. And what they did is meaning Sorek and Berg, they used different mutants to mimic that adaptation. So there's all these different curves of activity. And what I wanted to say is that Ned Wingreen and company, using the Monod-Wyman-Changé model, for which I already have also, I think I've done, a variety of vignettes on that. I may even have talked about this data collapse thing before, but I just wanted to show, that this notion of data collapse, of finding the right degrees of freedom, which in this case is this thing I'm calling F effective of C, allows you to see that there are many ways to achieve the same level of activity. You could have a changed Ki and Ka, you can have a changed Ei and Ea, you can have a changed concentration. All of those parameters can result in the same value of activity, and that same value of activity in turn can be exploited to get a data collapse. So here I labeled as the Bohr parameter. So, the summary then of what I wanted to say in this brief vignette was, I wanted to highlight this idea of we're really in the search for good coordinates. And so often we have these huge high-dimensional vectors, and the vectors, you could think of that vector as being in some basis, and my question is, how do I find a new basis so that that vector becomes simpler? And, those are mathematical words, but they often go with really, really deep and quite profound intuition. Like in this case, it's not just a mathematical trick. I mean, finding the correct coordinates really amounts to, if you like, bringing Fourier analysis to the table in like this super profound way, and in also a very beautiful way. So what we'll do in the upcoming vignettes is we'll talk about the nature of summary statistics. That will be a precursor to looking at the problem that I'm showing you on the screen now, which we'll do first by doing mechanics, as we just did, but then we'll secondly do it as a data analysis problem. And when we do it as a data analysis problem, we'll use PCA, and we'll see that principal component analysis causes us to discover the normal modes, if you like, in some form. So that's where we are, and I'll be back with those vignettes in the near